before the end of the talk and 2 minutes. Okay, so I'm very glad to introduce you Marian Capinski from Krakow, the AGH University of Science and Technology, who will speak on a topological mechanism for diffusion with application to the elliptic restricted three-body problem. Thank you.
Thank you very much. It's a great pleasure to be here. Thank you to the organizers for giving me the opportunity to give this talk. This is joint work with Marian, who is also here at this conference, probably on the audience. So what is the plan of the talk? I would like to talk about diffusion, but given the time constraints, my plan is to restrict to the simplest setting that is possible. So what I will do is I will start with some very low dimensional motivating examples, and the dimensions will start from 2 and build up to 4, which is the minimum that I will need for my mechanism. I will use then this setting, this simplified setting, to state the result. I will mention just a few words about how we verify our assumptions, and then I will move to the elliptic restricted three-body problem. And in fact, the whole thing is set up so that these examples are in fact exactly what we observe in terms of dimensions and in terms of the dynamics as what happens in the elliptic problem. So this is the plan. Okay, so what are my examples? And I'm going to start with a very modest situation where I have a map. So all my discussion is going to be in terms of discrete dynamical systems. So I'm iterating a map. This map has a hyperbolic fixed point, unstable manifold, stable manifold, and they intersect transversely, which leads to the usual horseshoe. Okay? So what is going to be important for me? What is going to be important is that if I single out a region along the unstable manifold and draw a one-dimensional curve, then what I can do is I can propagate the fragment of this curve by the map to the point where it intersects the stable manifold, iterate it again, iterate it once again, and what it will do, it will come back again as a well-aligned horizontal curve. Right? If I choose a different fragment, then it can pass through the alternative point of intersection, do it a couple of times, and I come back with a fragment that is again a curve. I will refer to these curves as horizontal disks because they are going to be flat. So in the whole talk, when I say horizontal disk, this is a one-dimensional curve in some space. Okay? Okay, so what is important for me, I mean, the trivial fact is that I return after different numbers of intervals. Okay, so let's build this up into something more interesting. So my next step is to talk about the map G that does exactly the same on the xy coordinates. So here I have this intersection, right? But on the angle coordinate, it is just a rotation. Yes? So in this situation, I'm not drawing the full picture because it will get messy, but when I start with the single curve, I have this fragment that returns, but after 3 iterates, so it kind of maybe spins around but returns here, and this guy takes 4 iterates, it takes slightly longer. They come back at a different angle. Okay, but if my angle is irrational of rotation, I can do this again, again, again. I can propagate when I'm close to the point that I iterate these disks more than 3 times. Maybe 5, 6, 7, 8, 9, 10, until I come back to the same region. So what I'm trying to say is that for any horizontal disk, I can choose its fragment, which will return to the neighborhood that I started with. Yes? Okay, and what does this have to do with diffusion? Nothing yet. I need to add one more coordinate. Okay, so what I'm going to do is I'm going to do on the first 3 coordinates, I'm doing the same picture, and on the last coordinate, which I call I do nothing. This remains constant. Okay? But this is for what I'm considering is I'm considering a family of maps. And this is for the map which has parameter epsilon equal to 0. So this is the unperturbed map. Okay? So for the unperturbed map, I'm assuming that on the first 3 coordinates I have this picture, where I have the homoclinic tangle and movement along the and on the angle, but on the I-coordinate I do nothing. So what does this have to do with what we're talking about here? Well, these I and theta, these will be action angle coordinates. Yes? And x and y, these are the hyperbolic coordinates. Yes? This is precisely the setting that I will want. And for epsilon equal to 0, let's say that we have an integrable Hamiltonian system, I is present. Okay, so what is the objective? The objective is, what conditions will ensure that for any epsilon bigger than 0, I'm going to have diffusion in I? Okay, so I'm repeating my map. For epsilon equal to 0, I have this. And here comes the statement of the main result, which says that if I have a setting that when I have a horizontal disk, I can always choose its fragment so that it will come back as another horizontal disk back to the same domain. And so this is the first assumption. And the second assumption is, for the fragment that returns, I need this condition to be satisfied. So let's have a careful look at this condition because this is the key issue, right? So this phi, this is the projection onto the action, right? So this condition says any point that returns after n iterates is going to increase in action. This is what we started with, by a factor of c, some constant, times epsilon. So this is my key assumption. Two assumptions. I can return. Second assumption. If I return, I'm increasing in energy by factor c times epsilon, right? So what is the claim? The claim is that for every epsilon bigger than 0, I can choose a point, starting point, which has energy equal to 0. I can choose a number of iterates such that after this number of iterates, I'm going to increase in energy by a factor of 1. Of course, this number of iterates needs to be larger as the epsilon is smaller. Right? I'm not saying that I have a uniform. Okay, so how does the proof go? Well, the proof is almost automatic, right? I choose a point with 0 energy, iterate it, come back, right? It has increased by c times epsilon. Okay, I need to iterate it again, 1, right? And again, at least until my c times epsilon is piled up to 1. Okay? This is the gist of the proof. Okay, very good. But what I've been drawing here is I've been drawing horizontal disk, and I said, oh, if I can show this, if I can show that. So the question is, how do I actually control this horizontal disk for a particular system? And here, what I do is, what we do with Marian, is we use two tools, which are correctly aligned windows or covering relations or conditions. So what I will say is that a map satisfies a covering relation. So I have two boxes. These are going to be three-dimensional pictures because these are the simplest to draw, right? So one box, the box N1 is covered by the box N0 if the image of the box is topologically aligned as in this picture. So what is important is that I have one-dimensional expansion, so the edges get mapped outside and the rest remains inside, right? Another condition that I need to control horizontal disks is that my map satisfies conditions. Right? So if I start with a point P, attach a cone of a given slope to that point, compute f of P, attach a blue cone of the same slope, that the image of the green cone is going to get mapped inside the cone attached at f of P. Both these conditions are satisfied if you have hyperbolicity. Right? So, in fact, if you have expansion in this coordinate. And what is important for me is that these conditions are verifiable using interval arithmetic. So for the first one, all I need estimates on the images, right, where things align. And to get conditions, I need estimates on the derivative of the map. And this is sufficient to check these, but I don't have time to go into details. So what does this have to do with our story? Let's say that I have a horizontal disk and I want to state that it gets propagated as I want, right? So the topological image of this horizontal disk is like so, right? But if I start with a disk that is aligned with, in terms of these cones, the cone conditions ensures that this doesn't wrap around or do something crazy, right? So what I can do is I can restrict my attention to the part that stays in, right? Limit it, and if I need, propagate it again using these windows as my construction. And this is what we do. Okay, so what is the application? Right? So the application is the elliptic three-body problem. So, I mean, I don't need to explain what is here. Maybe I'll just say that the eccentricity, which I denote as epsilon, is my perturbation parameter, right? So this is in the framework of pulsating coordinates, right? And we see that the epsilon appears here. So when eccentricity is equal to 0, this Hamiltonian is autonomous and energy is preserved, right? So what I want to say is if I have any eccentricity that is not 0, I have increase in energy. So this is the goal. All right. So let's see how these things work, right? So we needed to choose some particular system, and we chosen a Neptune-Triton system. And for epsilon equal to 0, you can do many things, right? Because it's well known. And we have chosen one Lyapunov orbit that has two homoclinic orbits. Just choose two. And what we do, I mean, this is an ODE, right? And I was talking about maps all the time. So what is my map? My map is a Poincaré map from section y equal to 0 to section y equal to 0. So on this picture, y is the vertical one, right? So I'm, let's say, starting here, wrapping around the Lyapunov orbit, wham, I'm hitting the section. So this is my map. So all the sets which I need to propagate my disks are going to be constructed on this section. But let's do something that is really simple first. Yes, so the simple thing is not to treat the elliptic problem, but do the circular one. Right? So if we do the circular problem, then we have 4 coordinates to start with. I drop 1 because I'm doing a Poincaré section, right? But wait, the Hamiltonian is preserved. So in fact, I have a 2-dimensional system. I don't need to treat the Hamiltonian, right? So what I do is this section green is in fact 2-dimensional. And on this two-dimensional section, I can construct these sets and check, okay, so I start with the initial box, it gets mapped, stretched along the Lyapunov orbit. Here I can choose 2, right? Depending whether I want to come back faster, this will be this N1 which is in blue. If I want to come back slower, this is the N1 in red. And you can note that here I have 13 iterates, here I have 15 iterates, right? And what I do is I spin around these homoclinics and come back to this, to cover the initial set. And this ensures that my horizontal disks get propagated as I want. Important thing is that we are in 2 dimensions. This is precisely the toy example that I was talking about. We start with a 2-dimensional map, right? Then we add perturbation epsilon bigger than 0, right? And we have this picture. We've added the angle, which is the true anomaly, right? We've added the h, which is the energy, right? This is exactly the setting that we discussed for our simplest statement of the diffusion mechanism, right? So here comes the coordinates, right? We start with these, drop y because we have a section. We can swap the py and change it into Hamiltonian. Then we can maybe choose coordinates to align the hyperbolic directions, right? And maybe just some normalizing, right? So that we have the energy from 0 to I star, right? So this is what we do. Okay, so what is one feature that is very important for us and very helpful? That these homoclinic orbits, they were not chosen randomly. So they were chosen, let's focus on this picture. They were chosen so that if I start with the horizontal disk here, and I return back to my set U, the angle, theta, increases. So I move a little bit to the right. Yes? So this is what is on this picture. If I start with some angles and I come back, I tilt a little bit to the right. What does this plot represent? It represents the derivative of the image of the energy as I return with respect to the parameter. Right? So if I choose these angles, so choose this box, then in fact I will increase by a certain factor. Okay? Now, how do we check this? We choose some boxes, we do the covering construction, right, and the box tilts to the right. The important thing is that if we choose these angles, we can use the second homoclinic, because it has this property that the angle tilts to the left. So and again, we have a good bound on the energy with respect to epsilon. So in total, whichever horizontal disk I choose, I can always choose the appropriate homoclinic so that I come back to the same set, and at the same time I have control over the increase of energy, regardless of the homoclinic that I choose. Right? Okay, so what is the result? So we take the Neptune-Triton system, particular mass. We choose the eccentricity from 0 to 10 to the minus 9, and we can prove, using interpollar arithmetic rigorous result, that we have increase in energy by factor of 1/2 10 to the minus 9. So let's maybe try to have an optimistic statement first. The optimistic is that this is an explicit range of epsilons. So the usual diffusion statements would say, for perturbations sufficiently small, we will have this and this and that. But it will not say how small the small is. Here we say this small. Right? So this gives an opportunity to continue using some other methods, or you can actually glue this. Yes. Okay. Oops. And so this is bad thing in terms of that this is small, and another bad thing is that this number is also very small. So we have the increase in action of factor of 10 to the minus 9. If you translate it into the real life distances, I think this would be proper, right? So this is how the result works. But what you can do is you can put it on a cluster, and you can cover much larger distances. So this computer assisted took half an hour on my laptop. Right? So this is the tool that we used. Okay, so let's just finish with some comments. The good thing is the explicit range of parameters. You can cover larger ranges if you iterate the procedure. This is we always have computer assisted tools in mind. We have explicit time on the diffusion. And this is some constant C divided by epsilon. What I did not mention in this talk at all, but what we do, is we, in parallel, can prove that we have symbolic dynamics. Moreover, for those orbits that we have symbolic dynamics, we have the bound on the Hausdorff dimension of the set that actually performs these symbolic dynamics. And the method, as it is written, is not restricted to low dimension like this. This is a general diffusion mechanism that can be applied in higher dimensions. Thank you very much.
There is time for one very, very short question and remark.
Maybe Daniel.
No.
So,
Now, everybody can ask him questions during the lunch time, so... Okay, so Ugo, you...
So the question is it conceivable a comparison between your approach, your results, and the results described by Rossio Paes about her work with Massimiliano and Christos? I mean, what is the point to me is that you describe a particular type of diffusion. They have results basically on samples of orbits and then the diffusion, and a semi-analytic results that cover very well the result. So I wonder if your mechanism is optimal, and maybe a comparison could highlight this, but maybe I'm wrong.
So I have absolutely no comparison because we have not made any comparisons, and I will never claim that my approach is optimal. So that would be an honest answer. I believe that this diffusion mechanism is cooked up to a particular setting. Right? This is not a general, but this diffusion mechanism is going to be present in most examples from celestial mechanics. So I don't know how these methods will compare. That is my short answer.
Okay, thank you for the short answer.